Hello, welcome to another lecture on formal methods. Today I'm going to continue discussing Bayesianism, and I'm going to focus on some of the criticisms and challenges to Bayesianism, and on some of the complications that arise when one tries to respond and accommodate these criticisms. This isn't just to point out the limitations of Bayesianism or even to suggest that Bayesian methods are deficient or problematic. Getting to know the things that one might criticize about a position, any position, but in this case, the Bayesian position, and getting to know the possibilities of responding to these criticisms um, is often a very good way to get to know this position itself in more detail, and that's why I will be going into a little bit of detail with regard to two basic problems of Bayesianism. I'm going to start with a problem that has played a great role in the critical discussions about Bayesian methods and Bayesian confirmation theory more specifically since the 1980s, and that's the problem of old evidence. So the problem here is that Bayesian conditionalization can only describe events. Can only describe the effects that a piece of evidence E has on a subject's degrees of belief when E is learned in a Bayesian learning event. That's um, how Bayesian conditionalization is designed. But this contains a limitation. The Bayesian methods can therefore not account for the confirmatory force of old evidence, where by old evidence we mean evidence that has been around and well known for a while, but whose relevance for a particular theory has only recently been discovered. And this may, for example, be the case if what's new is not the evidence itself, but what's new is the theory. So you to construct a new theory, and then you discover, this theory is very good in accounting for this interesting piece of evidence that we were not able to explain before we had this theory. So, and Clark Limmer here is the author who was mainly responsible for bringing this into the field of philosophical discussion in his book Theory and Evidence. There, the problem of old evidence is articulated, and in John Ehrman's book Bayes or Bust, there's lots of discussion of this, but there are other um, authors who discussed this in the 1890s and 90s. Ellery Eels, for example, and a host of other philosophers of science discussed this. So it's useful to introduce an example, not just any example, but the main example that philosophers of science and methodologists always talk about in this context, and that's the precession of the perihelion of Mercury. So the ellipses of planetary orbits are not robust, but they rotate slightly. This is called the precession of perihelion because, well, the perihelion is the point on the elliptical orbit that's closest to the sun. And this is not always the same point in space, but there's a precession of this. Sometimes this is also called apsidal precession. And this is expected also in Newtonian mechanics if the force between sun and planet is not exactly 1 divided by r, the distance, but differs slightly. And this is the case, amongst other things, due to the oblateness of the sun. The sun is not a perfect sphere, and also the influence of other planets. So far, so good. But in the mid 19th century, Urbain Le Verrier, an astronomer, noticed that the precession of the perihelion of Mercury is anomalous, in the sense that the elliptical orbit of Mercury rotates faster than what can be predicted from the known Newtonian causes, such as the influence of other planets and so forth. So it's not completely accounted for by Newtonian theory. There's an excess precession, and this is this is really like, we are not talking about huge amounts of movement. Yeah. So what astronomers soon found was in 100 years, the rotation is about 43 seconds more than what is expected or calculated from Newtonian theory. A second being the 60th part of a minute, and a minute is the 60th part of a degree. Yeah, so that's what we're talking about. In the years between 1907 and 1915, Albert Einstein articulated his general theory of relativity, where space-time is curved under the influence of massive objects, and this accounts for all the phenomena that had previously been attributed to gravitational forces. He soon understood that in general theory of relativity, orbits around a central mass would not be stable ellipses, but would generally include apsidal precession, or precession of the perihelion. And he then calculated what the apsidal precession for Mercury should be according to general theory of relativity, and found exactly those missing 42 or 43 seconds per 100 years. This is generally considered one of the most important empirical confirmations of the general theory of relativity. Here's a quote by Einstein himself from the paper where he presents this result, the fact that the theory can account for the anomalous apsidal precession of Mercury. He says, I found an important confirmation of that radical relativity theory. It exhibits itself, namely, in the secular turning of Mercury in the course of its orbital motion, as was discovered by Le Verrier. So, to explain why all this is a problem for the Bayesian, look again at Bayes' rule. Probability of, so the posterior probability is calculated by the prior probability of H given conditional on E. And we're using Bayes' theorem to calculate this. But now consider that E is not something that is learned, but something that is already known. Then the prior probability of E, this factor here, should be 1. This is already known. And hence, the new probability cannot be greater than the old probability. Yeah? The only way that this, all these factors are between 0 and 1. So the only way that this whole term could be greater than this would be if this denominator is smaller than 1. And the only way that it can be considerably considerably greater than this term alone is that this would be considerably smaller than 1. So hence, there can be no confirmatory effect of E on H if the prior unconditional probability of E is already 1. That is, if E is already known. Note that the confirmatory effect of the case with Einstein and the Mercury perihelion precession is considered to be strong and great, not just a little bit confirmation or something. So at first, there just doesn't seem to be any way that Bayesianism could account for this phenomenon, could somehow incorporate this into the Bayesian theory of confirmation. But of course, Bayesians have tried to think of solutions for this. One solution that has been proposed is that, well, the basic idea here is that the surprising thing that is learned in the case, in Einstein's case, for example, is not the fact itself that the planet of the Mercury planet, the Mercury has this and that precession of the perihelion, but what is surprising is the fact that E is a consequence of H. The fact that this is accounted for by the theory. That is what is learned, and that is what is new. Now, this is not easy to accommodate within the Bayesian framework because for subjective interpretations of probability, the assumption is always that coherent degrees of belief imply that the rational subject always knows all logical truths, because that's just a theorem of probability theory. Logical truths have probability 1, and that is called logical omniscience sometimes. So the Bayesian framework is such that it's always basically assumed that the agent knows all logical truths and has degree of belief 1 with regard to each logical truth. Obviously, this is an idealizing assumption, and it's not. This is an unrealistic assumption because normal agents do not know all logical truths. Ask yourself. But so it's clear that this is somewhat of an idealization, and so there may be some independent reasons to think about how you may relax this assumption. But the problem of old evidence somehow aggravates these concerns, and so in the 1980s, people started to think, well, how can we perhaps relax our logical omniscience? And Daniel Garber was one of the people who tried to do this. His idea was to relax the assumption of logical omniscience in such a way that the fact that E is a logical consequence of H is something that can be learned. So the fact that, for example, the precession of the Mercury perihelion can be derived from the general theory of relativity is something that can actually be learned in the framework. And then, of course, to show that for cases like this one, the confirmation, that is the rise of the raising of degrees of belief that happens when we add this logical fact to the conditionalization is great. So by realizing that E is a consequence of H, the conditional probability of H given this realization, and we know that the evidence is there, is greater than just the conditional probability of H given the evidence. So it's remarkable enough that you can even do this in some way. That is that you can develop formal frameworks for imperfect Bayesian reasoning. So Bayesian agents that have imperfect knowledge of the logical truth. But you can actually develop some such frameworks, and this was achieved by Garber and also by two other papers that were also published in 1983 by Ilkka Niiniluoto, a Finnish philosopher of science, and Richard Jeffrey, the Jeffrey of Jeffrey conditionalization fame. It turns out that even once you have these frameworks, it's far from trivial to derive this. It's not so easy to show that this is something that's generally the case. And it cannot be done, well, it can only be done on the basis of some pretty strong assumptions. But that's perhaps not the biggest problem of this approach. The bigger problem is probably that by relaxing logical omniscience, you are really sacrificing quite a lot about the original appeal of the Bayesian framework. Garber's framework, for example, permits situations where the statement that E is a logical consequence of E has a degree of belief of smaller than 1. So this is not yet known. And at the same time, the agent assigns probability 1 to a sentence of the form H prime, if H prime, then E prime, where H prime and E prime are constructed by means of logical constants in a completely analogous form to H and E. And so coherent or purportedly coherent agent is such that he does not know this, but he knows a tautology that is absolutely analogous to this. And so the full connection between permitted probability distributions and coherence that we have in the original Brainshield framework is lost. Also, it's odd in this solution that the general theory of relativity in this view seems to be confirmed not so much by the phenomenon of absidial precession itself, but by the mathematical fact that you can derive the latter from the general theory of relativity. Yeah? What's confirming the theory is not the empirical fact that Mercury has this anomaly, but the mathematical fact that this follows from the theory. And that's somewhat strange that what the confirmatory effect is ascribed to this mathematical fact. So a completely different take on the problem of old evidence was suggested by Colin Howson. Hausen uses counterfactual degrees of belief functions to deal with the problem. He suggests that to assess the evidential value of some piece of evidence E for some hypothesis H, Bayesians should not reconstruct scientists' actual degrees of belief, but a counterfactual probability distribution. So, namely, he recommends us to assess evidential support that the evidential support that E now gives to H by looking at how an agent would change her degrees of belief with regard to H if she now were come to know that E. So pretend that we would be learning E in this moment and then conditionalize on E and um, and see what happens then. What's the confirmatory effect? So that way, of course, the prior unconditional probability of E does not have to be 1 because we are pretending that we do not yet know that E. So this pretending takes the form of a fictitious probability distribution that does not incorporate the entirety of the agent's actual prior knowledge, which would include the knowledge about the perihelion of Mercury, but somehow her knowledge K minus E. So retract E from the body of knowledge, pretend that this is something we do not yet know, and somehow construct the distribution of degrees of belief that the agent would have if he did not or she did not yet know that, and then use this probability distribution to do the conditionalization. That's what Hausen recommends we do. This is a good moment to mention the principle of total evidence. The principle of total evidence is a principle that is normally assumed by Bayesians, and not only by Bayesians, it is considered to be an important principle of inductive inference and inductive reasoning ever since Rudolf Carnap discussed this, started discussing this basically in the 1950s, but there's a paper from the late 40s where he already suggests it. And the principle is basically this is a paraphrase. In assessing the confirmation of hypotheses and in making inductive inferences, the totality of available evidence should always be used. It's easy to understand why this is so. I want to motivate this a little bit. And by way of the example of inductive inference. The main feature of inductive inference that is important for the motivation why we should heed to the principle of total evidence is that inductive inference is non-monotonic. What does this mean? Well, non-monotonic means that adding additional premises can weaken the strength of the inference. So you have some piece of inductive inference and you think it's pretty good. And then you add another premise and suddenly the inference is not good at all anymore. This is something that cannot happen to you when you do deductive inference. Yeah, if you have a deductive argument and it works and it's valid, it stays valid. if you can add as much information to the premises as you want, as long as you don't undermine any of the premises, you don't take anything away, the argument will remain valid. We saw in the beginning of our course that even if you add premises um, that contradict the premises that you already have, the argument remains valid because from a contradictory set of premises, every conclusion follows logically. So deductive inference is monotonic, but inductive inference is non-monotonic. Consider this following example to make the point somewhat vivid. So this is to be understood as an inductive inference based on known statistical facts. Pretend that you know all the relevant statistical facts to assess this kind of argument. So Otto is 50 years old. He's been living in the Bavarian countryside for almost his entire life. Otto has very conservative views and values. Otto is a devout Catholic. Otto is heterosexual. Otto is friendly, outgoing, well liked, conventionally attractive, and professionally successful. And you conclude that Otto is very probably married, because that's what a conservative and so on and so forth guy in the Bavarian countryside would be. Now, you may assess this as more or less strong an argument. Perhaps you think, it's not so strong, but it doesn't matter. The thing that matters is if you add just one little piece of additional information, namely that Otto is a clergyman by profession, the argument would definitely be weakened. And so the resulting argument by adding this one piece of information is not a good argument at all anymore. The conclusion is not supported by the set of premises. So that's why you should for good inductive inference, we always need to consider as much information as we can, because it's not like in deductive reasoning that at some point we're just done and we don't need more information. We can always use more information, because more information could always potentially require us to revise our assessment of the argument. And in a nutshell, this is why inductive inference is so complicated and also so interesting. And this is why philosophy of science is so complicated and also so interesting, and also so a little more interesting than logic. In Bayesian terms, the principle of total evidence takes the form that degree of belief functions should always represent actual degrees of belief of rational agents that incorporate all the background information available. So that, what does this incorporate mean? It means that we are assuming that all the background information that is available to the agent has already been incorporated in his or her degree of belief function by means of Bayesian learning, by conditionalization. And if you put it like this, it becomes obvious that Hausen's proposal seems to militate against this Bayesian version of the principle of total evidence, because Hausen makes this suggestion of saying, well, let's pretend that the agent does not yet know that E. Now consider for a moment how Colin Hausen motivates this. According to Hausen, the need to consider the degree of belief function that reflects the totality of available evidence without E, except E, retracting E, arises for every learning event, because really, realistically speaking, the moment that anyone is in the position to conditionalize on E, they always already know that E. So by doing Bayesian conditionalization as we do, we always pretend in that moment, or we pretend, okay, in the moment of conditionalization, we pretend that they do not yet know that E. And then only as a result of the conditionalization, E's uh, degree of belief is raised to 1 or to some other value if you do Jeffrey conditionalization. So that's basically Hausen's rationalization for taking this exception to the principle of total evidence. But nonetheless, it's clear that Hausen's proposal is a move away from orthodox Bayesian thinking. But there may also be other separate good reasons to relax the principle of total evidence, as some Bayesians have suggested, for example, Brandon Feitelson. So let's look at Hausen's solution again. First of all, it's not as simple as it looks. This idea here, I mean, I've sort of already hinted at by using this somehow, this idea is easy to say, but not so easy to also put into action. The problem is it's not one problem, or the main problem is it's not clear how to determine what the fictitious body of knowledge K minus E even is. If you look at a body of knowledge, if you look at, if you conceive of a body of knowledge in terms of a reasonable axiomatization of this body, by which I just mean a very simple thing, namely a reasonably surveyable set of propositions such that the whole body of knowledge can be derived from this set of propositions. That then you soon realize that if you just think of K minus E as just taking the proposition E out of this set of propositions, then different axiomatizations of the same body of knowledge lead to different results when taking E away. Consider this very simple toy model of a body of knowledge that is just axiomatized by two axioms. The first axiomatization is just the two sentences E and F, and the other is the two sentences E and if E then F. Think for a moment, I mean, to realize that these two sets are logically equivalent, that exactly the same. By which I mean to say that the sets of propositions that can be derived from these two sets are exactly the same. Yeah, every sentence that is a logical consequence of these two sentences is a logical consequence of these two, and vice versa. But if you take E away from each of these sets, you have different results. K1 minus E still contains the proposition F. K2 minus E does not contain the proposition F, and also the proposition F can then not be inferred anymore. So perhaps then you might say, well, then it's perhaps better to think of a body of knowledge not in terms of an axiomatic theory, but rather as a bulk of beliefs, a set of beliefs, including all kinds of beliefs that are already inferential in nature, that are already inferred from sort of the more basic kinds of belief, and the agent may already have inferred. That's not only can be inferred, but that the agent has already inferred with the aid of, for example, E. But then it's not clear that just by taking E itself out of this huge body of knowledge, that this will even change very much about the system of beliefs. If the system of beliefs contains also all kinds of inferences that the agent has already made on the basis of E, the E will somehow remain in this body of knowledge, even if you take the isolated proposition E itself out. And for example, the probability, the unconditional probability of E may have to remain pretty high, very, very high in the remaining set if you just take the isolated proposition E out. And if the set still contains many close inferences from E. So you have to find a way of getting rid of these closely related pieces of knowledge too. And this is a science in itself. And I'm not only speaking figuratively here. It is actually there's actually a theory or a whole body of work that is related to these kinds of problems. It's called belief revision theory, and there's a whole literature on this on exactly these kinds of problems. And they do have proposals of formulating rules of how do you do this. It's called retraction, belief retraction. What's the most coherent and convincing way of retracting a singular proposition from a body of beliefs? But there's no uniquely determined right answer of how to do this. Even in belief relation theory, there are different proposals. So this is kind of a technical problem of Hausen's proposal that already indicates it's not quite as easy as it seems. There's but there's also a deeper problem that you may consider if you look back at Glimmer and how Glimmer proposes or presents the problem of old evidence in the first place. He presents it as a deeper problem, and I'm now trying to paraphrase the thrust of his criticism. Glimmer thinks that there's a core to the problem that all these kinds of attempted solutions don't even start to get at. According to Glimmer, between a theory and a piece of evidence that's relevant for this theory, there must be some kind of structural connection. And what the Bayesian theory does is they just look at how rational agents raise their degrees in belief in the theory when they learn that E. And this is not something that's constitutive of this relevant structural connection. It's just at best a consequence of it, of this structural connection. And as Glimmer puts it, it's an epiphenomenon. And so what Bayesian confirmation theory does is it studies this epiphenomenon. It doesn't really get at the real task, which is to describe and analyze this structural connection between theory and evidence. And the problem of old evidence just brings this to the fore. It shows how conditionalization cannot really capture the structural connection between theory and evidence, because these special cases where the evidence is already known and therefore you cannot really conditionalize on the evidence anymore, and in Bayesian terms there is no raising of the degrees of beliefs anymore. This just goes to show that it's not really about this raising of beliefs. It's clearly the case that the kind of relation that exists between the general theory of relativity and the anomalous precession of the Mercury perihelion is exactly the kind of relation that we need to understand, even though if there is no conditionalization here and no raising of degrees of belief when you suddenly chance upon this piece of evidence. So in Glimmer's view, really the problem of old evidence is not just a technical problem for these specific particular cases. It's not just like, oh, Bayesianism can't account for these freak historical cases like the Einstein-Mercury perihelion case, but it is these special cases just offer us a glimpse of a deeper problem, of deeper inadequacies of the Bayesian approach, because they don't really get to the core. They just study something that is just an epiphenomenon, that is just something that the confirmation relation brings about, but it's not the confirmation relation itself. So I leave it to you whether you buy Glimmer's gloomy assessment, but in any case, the problem of old evidence remains one of the most difficult and challenging problems for Bayesian confirmation theory, and alternative solutions to it that are often variants on um, what I've talked about so far is are still being discussed. So um, perhaps so I want to also talk about another challenge to Bayesianism, and this is perhaps even the even bigger problem, and it's the problem of subjectivity, or the problem of the priors. And the problem just is that Bayesianism is based on the subjective interpretation of probability. So this is really a kind of problem that Bayesianism doesn't even try to hide. Yeah, it's that's just what Bayesianism is, or we'll see for a moment. There are people who disagree, but the standard orthodox Bayesian view. So and this so this brings subjectivity into Bayesianism. Yeah, and this is the most problematic, as I've said many times, in the case of prior probabilities, and that's where it's problematic even for tempered subjective Bayesianism. Tempered subjective Bayesianism being the idea that whenever we have some knowledge or information about objective chances, we use this information to inform our degrees of belief and to assign probabilities. And we can often do this to assign probabilities, or yeah, this, or also the what the content of the theoretical beliefs themselves. They make some clear statistical claims, and we can use those to assign non-arbitrary values to likelihoods. Yeah, so likelihoods are generally not so much the problem, but the prior probabilities, the prior probabilities of the hypotheses are, and that's why it's also often called the problem of the prior. So what's the problem? The problem is that different scientists may start from different distributions of prior probabilities, and then even when they work on the same data, when they analyze and draw conclusions from the same data, the same evidence, they will arrive at different posterior distributions when they start from different prior distributions, and then they will possibly make different conclusions. And this is perhaps something that we don't want from a theory of scientific inference, because it seems to bring an element of arbitrariness, of subjectivity into it, and in that sense, maybe a bit of a letdown. So there are different Bayesian reactions to this. The first I want to talk about is a reaction that does not uh, um, rebut this in any sense, but that kind of relativizes its importance. So this reaction is based on a number of convergence theories, convergence theorems. I'm sorry. And sometimes these theorems are also called the merging of opinions theorems. And so the main claim is in time the priors wash out. So what these convergence theorems say is that posterior probabilities of rational agents learning the same evidence by means of Bayesian conditionalization will converge in the long run, even if they start from different prior distributions, as long as they agree on which propositions are assigned probability 0. So you have two agents start from different prior distributions, but the distributions are not too different in the sense that they have zeros in the same places. Yeah. Or maybe no zeros at all. That's also one way. They could have zeros in the same places, but if one of the probability distributions assigns 0 degree of belief to any proposition, the other must too. Under this condition, it can be proven that there's an asymptotic behavior if both agents learn the same evidence and conditionalize by Bayesian conditionalization, then there will be convergence. And the convergence is uniform. It holds for all the propositions that the agents assign degrees of belief to. As you can see, so these are a few papers that where these results are presented. The first three. I've also included Savage here, Foundations of Statistics from 1972, because he shows a related result, and he shows that under certain conditions, one can even say that the true hypotheses are increasingly confirmed in the long run, and the false ones are increasingly disconfirmed or invalidated by Bayesian confirmation. For example, in processes such as judging the fairness of a coin, yeah, Savage kind of shows that Bayesian conditionalization in these kinds of processes doesn't just lead to convergence between different agents, but also to convergence to the truth in the sense that the hypotheses, the statistical hypotheses that the agents have about the behaviors of the coin, for example, actually represent the objective chances. So these theorems can be used to defend Bayesianism against the subjectivity charge in an obvious way, I guess. I mean, the differences in prior distributions matter only in the beginning, and as time passes and as more and more agents learn more and more about the world, the differences matter less or they wash out, is how it's often put. But there are some very important limitations that one has to keep in mind. The perhaps seemingly innocuous premise that the agents have to agree on the zeros, if you think about it, this may actually be not such an innocent assumption, because it means that agents have to have total agreement on what's possible and what's impossible. You know? And so this is not a very good model, I think, not a very realistic model of the kinds of agreement that we find in scientific communities, for example. But that's not perhaps the biggest problem. The other problem is perhaps the bigger problem, namely the question of what does in the long run mean. So the theorems themselves have nothing to say about how quickly posteriors will converge. And unless you make some additional assumptions about the spread of priors, so how distant the priors are allowed to be from each other. And so in practice, in practice, conclusions from small sets of data or medium-sized sets of data matter to us. Yeah, and the agents that learn medium-sized sets of data may still have may still draw different conclusions from them in practice when they start from different prior distributions. And so this the realization that they would converge in their judgment if they had huge or infinite data at their disposal is little consolation, perhaps, in this respect. So another more radical reaction to the subjectivity problems is to move to objective Bayesianism. And by objective Bayesianism, I mean all the kinds of attempts to give objective prior probabilities, or at least objective restrictions for the initial distributions. So Edwin James is a pioneer of this line of objective Bayesianism, and his basic idea from the late 1960s is that in situations where agents have the same initial information, shouldn't they also start from the same prior probability distribution? Shouldn't we be able to identify one uniquely rational probability distribution that's rational for them to start from? And so there's still some fans of this approach around. Perhaps the most influential author now is John Williamson, John with Jon. So if you spell out this attempt to have non-arbitrary, somehow uniquely determined correct probability distributions to start from, you inevitably need some variety of the indifference principle. And the indifference principle, we've encountered the indifference principle before when we discussed the classical interpretation of probability, and in a way these ideas are distant heirs of the classical interpretation. So the indifference principle means that in the absence of any additional information, all probabilities must initially be considered, all possibilities, must initially be considered equally probable. Unless we have some information to distinguish between different possibilities, we need to apply the principle of indifference. So this is sort of a primitive version of this principle. Modern varieties of objective Bayesianism usually make use of the entropy concept from information theory to spell out which is the uniquely rational distribution. So the distribution should be the one with maximal entropy, that the maximal entropy that the data permit, where this is an information theoretic entropy concept based on Claude Shannon's information theory. And it boils down to selecting the least informative possible distribution over the partition of possibilities that you use. But the technical details of these I'm not going to go into the technical details of these approaches, and I don't think they matter for the purposes of this lecture. I just want to, well, basically just tell you that this is a thing that exists. But I will also want to point out a principle limitation of this approach. And to point out this problem, or to get to know this whole approach a little bit, it's enough to understand that it's always a more or less distant variety of an indifference principle that is applied in objective Bayesianism. This is a time-honored aspiration to try to find objective probability functions. In a way, Rudolf Carnap, who pioneered the application of probability to confirmation theory, and whose book that I've mentioned several times already, The Logical Foundations of Probability from 1950, contains already many things that are now standard features of the Bayesian approach. He also attempted to give objective constraints on initial probability. He conceived of this as a logical probability function. And this is generally not considered to be convincing in the end. And well, all these attempts suffer from one severe problem, and that is that when you transfer the idea of distributing probability equally amongst all the possibilities, when you transfer this to the continuous case where you have infinitely many possibilities in a continuous parameter space, then the principle of indifference leads to different results depending on the chosen parameterization of the problem. And so unless you have some good reason to say this is the right parameterization of the problem and this is the wrong parameterization, it leads to an impasse. You don't know which one is the indifferent distribution. So the basic problem here is that all these principles of indifference or symmetry or minimum information, they take it for granted that the world comes carved up into a set of possibilities, and then the principle of indifference somehow tells you to spread out probability evenly over these possibilities. But this line of reasoning is problematic, and it clearly breaks down in a continuous case. And this is this breaking down, this dependence on different parameterizations is called Bertrand's paradox, and it's long known. It was known in the 19th century, long before Bayesianism was discovered or discussed. And I'll illustrate Bertrand's paradox by a very simple example and for a very simple-minded application of an indifference principle. And so, well, here's the problem again, or the paradox. It's called a paradox, but it's not really a paradox, but okay. In continuous parameter spaces, spreading out probabilities evenly leads to different results for different parameterizations of the same problem that are not linearly related to one another. The parameterizations are not. So here's an example, a very example. Consider Otto again, or a different Otto, I don't care. He has a square garden, and the side lengths of the garden are somewhere between 4 meters and 8 meters. That's all we know. No longer than 8 and no shorter than 4 meters. That's the side length here. So what's the probability that the garden has an area between 25 and 36 square meters? There must be a probability there. So it's not guaranteed. It could be greater than 36 square meters. It could be smaller than 20. There's a finite probability here. Now, how do we solve this problem? we first have to parameter. We have to choose a parameterization, and I'm offered two parameterizations here, one by side length and one by area. So we haven't talked about probability for the continuous case. So I just very quickly, if you do this, if you have infinitely many, so there are infinitely many point possibilities, of course, between. So if the garden has side length at least 4 and at most 8, and there are of course infinitely many points between 4 and 8. So how do you then how do you treat probability there? You treat it by a probability density function. This is the W function here, and the the way that these density functions work is that the probability of any interval is always the integral over the function for this interval. Yeah? And the idea of applying the principle of indifference here would be to have just a constant density function over the whole interval. So the density is the same everywhere between 4 and 8. And this is so the blue line here represents the density, probability density function for this parameterization. So the parameters, the whole probability is distributed over this interval between 4 and 8, where we know somewhere between here the true side length of the garden is, and we say that probability, applying the principle of indifference means that the density is the same everywhere here between these values. And this exhausts all the possibilities, and therefore the integral the integral from 4 to 8 is 1. Yeah. So all the probability is distributed over this interval. And then if you want to know, so how high is the probability that the garden is between 25 and 36 square meters? That's of course, that means that the side lengths are between 5 and 6 meters, and that's this part. And if you calculate the integral for just this section of the function, then it's 1/4. Okay. Then, of course, you could do the same thing with a different parameterization, do parameterization by area. So just the same idea. So the area of the garden is between 16 and 64 square meters. And then you do the same idea. Okay, spread the probability out evenly amongst these possibilities. But the important thing here is that these parameterizations are not linearly related to one another. And so calculating the actual probability for this interval, then from 25 to 36 square meters, actually leads to a different result. Because 11 divided by 48 is not 1/4. And this means that this is a different probability distribution than this one. It's quadratically related to one another. So of course, objective Bayesians have some ideas of how to deal with this problem, but so far, no widely accepted solution has emerged. And so far, objective Bayesianism remains somewhat an outsider position in philosophy, at least. Although objective Bayesianism has more fans in the sciences, so there are people who actually try to apply Bayesian principles to data use and statistical reasoning in the sciences, in physics and in other sciences, and there objective Bayesianism is somewhat more of a popular position, but you can sort of see why. I mean, this is a philosophical problem. Yeah. So the philosophical problem is, well, there's no principled philosophical argument why one parameterization of the problem is uniquely singled out to be the true relevant one. Whereas if you have an application-oriented focus, you may easily see that certain parameterizations somehow more suggest themselves for practical reasons, and then you just go with them and so on. But in philosophy of science, subjective Bayesianism, or tempered subjective Bayesianism perhaps, remains the dominant position. And there we kind of, that just means that in a certain sense we live with the kind of subjectivity that is implicit in this, that is implicit in the framework of Bayesianism. And this does not mean, I mean, this does not mean that Bayesianism is totally subjective, of course. Bayesianism gives very strict, very, it gives guidelines on how to adapt an existing framework of degrees of beliefs to incoming evidence. And it has principles on how this ought to be done that are very well grounded in in rationality considerations, and it therefore clearly has important things to say about inductive inference and about probabilistic inference. It has to take prior distributions for granted, or it has to accept that prior distributions are not placing constraints on prior distributions are not within the purvey of this theory. But for example, if you compare this to deductive logic, it's kind of similar to how deductive logic has to take for granted that the truth of the premises is not the business of logic. Yeah? It has to assume that whether or not the premises are true is settled somehow by other concerns, not by logic. And similarly, Bayesianism just excludes, or I'd say the mainstream tempered subjective Bayesianism just excludes judgments about what's the right prior probability distribution from the purvey of what the theory aspires to do. So, okay. This completes what I wanted to tell you about Bayesianism. It's been just a fairly superficial survey of some of the main achievements, but also some of the main problems. And I look forward to talking to you about this in our video meeting.